Does this type of Olympiad problem with fractional powers make you feel uncomfortable? So today here we are going to see the approach we can use for solving this type of problems. So our first step would be to make the power, fractional power, into positive integer power. And for that we are going to substitute the value of x and such that powers get cancelled out and we get positive integers as our power. So let's see first that if we assume x is equal to p raised to the power 6, then when we put this value of x here, we get p raised to the power 6 whole raised to the power 1 by 2 minus p raised to the power 6 whole raised to the power 1 by 3 is equal to 4. From here, our fractional powers are getting cancelled out. A raised to the power m dot n it become. So it gives p cube minus p square is equal to 4. So now the question is how we are going to find this type of perfect substitution. So the answer lies in the LCM of the fractional powers. If the fraction would have been like 1 by 4 and any to the power y raised to the power 1 by 4 and minus y raised to the power 1 by 1 by 7, then our LCM would have been our substitution would have been y is equal to p raised to the power 28. So in this way we are going to decide the powers. Now let's move further. So now this expression can be written as p cube minus of p square minus of 4 is equal to 0. Now from here we can use two methods to solve this. Number one, as this is cubic expression, so without any substitution or without any assumption, we can solve this by rearranging the equation. So our first approach is without any substituting any value. So let's rearrange our equation, which is p cube minus of p square can be written as minus of 2p square plus of p square, and minus 4 can be written as 2 raised to the power 2, and it is equal to 0. Now from here you will see identity appearing, which is a square minus b square. So when we use this identity, we get p cube minus 2p square plus of p plus 2 times p minus 2 is equal to 0. Now, might be wondering that why we have used this expansion. The answer lies here, that when we take this p square common, we get here p minus 2, and in the right side by expanding this we are also getting p minus 2. That's why we use the expansion so that we can take things common. So this become p square to p minus 2 plus p plus 2 times p minus 2 is equal to 0, and now taking p minus 2 common, we get p minus 2 in the bracket p square plus of p plus 2 and is equal to 0. So either p minus 2 is equal to 0 or p square plus p plus 2 is equal to 0. From here we get p is equal to 2 as our first value of p, and from here first of all we are going to find determinant so that we can get whether it will give real roots or not. So to find determinant we use b square minus 4ac, and its property is that if it's give positive value, then our equation will give real roots, and negative, then it will give non-real roots, that is imaginary roots. So b square minus 4 is, b is the coefficient of p, and here the coefficient of p is nothing, so it will be 1. So 1 minus 4ac is 4 times coefficient, a is coefficient of p square, so here is nothing, so 1 times c is our 2. So it gives 1 minus 8, which is equal to minus of 7. As this is negative, so from here we are getting no real solution. So from this we get that we are getting only one value of p, which is 2. Now we have used the substitution that x is equal to p raised to the power 6. So x will be p raised to the power 6. So this is our answer. Now let's check whether this is correct or not. So when we put this value of x here, we get 2 raised to the power 6 over 1 by 2 minus of x raised to the power 6 power 1 by 3, and we are checking whether it is equal to right side, which is 4 or not. So again this cancel out, it gives 2 raised to the power 3 minus 3 to the 6. So 2 raised to the power 2 raised to the power 2, and on further it solving it gives 8 minus 4, 8 minus 4, which is equal to 4, and this 4 is equal to our RHS. Hence the value of our x is correct. Now let's move to the second approach, that is the approach used for solving cubic expression using root theorem. Using root theorem.